Assalamu alaikum, dear student. This is lecture number 2 of week number 5, and we are starting a new chapter, the fluid dynamics. First of all, we are going to see what are the learning objectives of this chapter. The learning objective of this chapter that indicates that what we will achieve after completing this chapter. So after completing this chapter, you should be able to discuss the application of Newton's second law to fluid flow. Also, you will be able to explain the development, uses and limitation of the Bernoulli equations. And also, you will be able to use the Bernoulli equation standalone or in combination with the continuity equation to solve simple flow problems. And also you will be able to apply the concept of static, stagnation, dynamic and total pressures. And finally you will be able to calculate various flow properties using the energy and hydraulic grade lines. So let's start the topics that we are going to cover today in this chapter are the introduction of fluid dynamics, Newton's second law. We will see how we apply the Newton's second law to a fluid flow. Then we will derive the Eulerian equation and then Bernoulli equation, and we will see the physical interpretation of the Bernoulli equation and its importance. So let's start the fluid dynamics. What is fluid dynamics? Fluid dynamics deals with the phenomena associated with the fluid motion. Fluid motion involves concept of force, acceleration and Newton's second law. So basically in the previous chapter, the fluid kinematics, we see that in the fluid kinematics we focus on the effect of force, regardless effect of force, that is acceleration, velocity and displacement, disregard to applied force or the reason of force. But in the fluid dynamics we consider the force as well as the effect of force. So whenever we talk about the force and acceleration, that means the Newton's second law will be there. So in this chapter we will also focus on some of the important definitions or important concepts. In general, fluid flow means net motion of a fluid molecules from one point in space to another point in space as a function of time. A small portion of fluid contains so many molecules and it is not realistic to account the motion of individual molecules. Instead of that, therefore, we assume that the fluid is made of fluid particles. Each fluid particle contains numerous molecules. We describe the fluid flow in terms of the motion of fluid particle. So whenever we talk about the fluid particle, that means that particle contains numerous molecules. So now let's see how do we apply the Newton's second law on the fluid flow and what are the consideration and assumptions we required to apply the Newton's second law. So in the Newton's second law, we know that as a fluid particle moves from one location to another, it usually experiences an acceleration or deceleration. So according to the Newton's second law of motion, the net force acting on the fluid particle under consideration must be equal to its mass times its acceleration, that is F is equals to ma. So now the first consideration we are going to consider under the heading of Newton's second law is the non-viscous flow. Okay, so in this chapter we are going to make some assumptions or consideration to apply the Newton's second law. The first one is the flow is non-viscous. So what does it mean? Consider the motion if fluid is inviscid. It means fluid is assumed to have zero viscosity. But we know that in reality there are no inviscid fluid. Since every fluid supports shear stress when it is subjected to a rate of shear strain displacement. But in many cases, the viscous effects are relatively small compared to the other effect, and it is often possible to ignore. For example, often the viscous force developed in following water may be several order of magnitude smaller than force due to other influences such as gravity or pressure differences. For other water flow cases, the viscous effect may be dominant one. Similarly, the viscous effect associated with the flow of a gas are often negligible, although in some cases they are very important. Now, the second assumptions we are going to make, that what are the type of forces that we are going to cover in this chapter. So we assume that the fluid motion is governed by pressure and gravity force only in this chapter. So other forces such as surface tension force, compressive force and turbulence force are neglected. So now the Newton's second law as it applies to a particle will become net pressure force on a particle plus net gravity force on a particle equal to particle mass multiplied by the particle acceleration. Okay, so here all other forces are neglected. The motion or acceleration is considering only due to these two forces. Now the third assumption or consideration we are going to make, the coordinate system. So definitely whenever we going to apply the Newton's second law to a fluid, okay, or any other object, we must define the appropriate coordinate system in which to describe the motion. So we know the available coordinate system, generally the fluid motion will be three-dimensional and unsteady. So three space coordinates and time are needed to be described. Usually flow geometry dictates which would be most appropriate. The most commonly used are rectangular or Cartesian coordinate and the cylindrical coordinates. So this was our third assumptions, and here you can see the picture of the Cartesian and the polar coordinates. So now the third assumptions we are going to make, the flow acceleration, that is AS and AN. So under the flow acceleration we know that the motion of a fluid particle is described in terms of its velocity. Okay, the motion of a fluid particle is described in terms of its velocity v. As the particle moves, it follows a particular path, okay, the shape of which is governed by the velocity of the particle. So whenever the particle moves in a path, and this path or shape is governed by the velocity of the particle, so the location of the particle along the path is a function of where the particle is started at the initial time and its velocity along the path. Okay, so here if the flow is steady, okay, so what is the meaning of steady? There is nothing change with respect to time. Nothing change means there is no change in velocity and there is no change in the fluid properties. Okay, so that means whatever is the fluid particle passing through this point 1. Okay, so here you can see if the flow is steady, each successive particle that passes through a given point such as point 1 as shown in figure will follow the same path. Okay, will follow the same path because there is no change in velocity and there is no change in fluid properties, because if the velocity is changing then definitely it will leave this path and it will take some other path, and if the velocity is constant but the fluid properties are changing, for example the density is changing, so definitely this particle will move upward or below this line. So that means if the flow is steady, the particle will follow the same path, okay, because the velocity is constant and the fluid properties are constant. Okay, for such cases the path is fixed line in the xz plane. So this is our xz plane, this is the point 1, and the fluid particle, okay, in the case of a steady state, is moving in a one single path. Okay, neighboring particles, okay, the other particles which are above it, okay, pass on either side of the point 1, follow their own path, which may be of a different shape than one passing through one. The entire xz plane is filled with such paths. Okay, so all the particles which are neighboring to this point 1, they will follow their own path, and the whole coordinate system will be filled with these lines, and these lines are called the streamlines. So streamlines are lines at which the flow velocity is perpendicular to the tangential to the every point on a streamline. So you can see that here. So consider this is our streamline. So this velocity is perpendicular, the tangential to the tangential at every point on the streamline. This is going to be tangential here, the tangential here, the tangential here. So wherever you will see the velocity, you will find the velocity is tangential to the streamline. Such lines are called streamlines. So now for steady flow, each particle slides along its path. Okay, for the tangential flow, each particle slides on its path and its velocity vector is everywhere tangential to the path. The lines that are tangent to the velocity vector throughout the flow field are called the streamline. So these lines are called streamlines. Here you can see there is a cylinder and the waters are passing over this cylinder and form a streamline. These lines in practically we cannot see, but the streamlines are also called the imaginary lines. Okay, we don't say that the lines are passing like this, but we assume that the particles are moving in a layer, okay, as shown in the picture, and these lines or layers are called streamlines. So here the distance along the streamline is related to the particle speed. Okay, so definitely it is velocity is the change in position with respect to time is called speed or velocity, and the radius of curvature is related to the shape of the streamline. Okay, so whatever is the shape, you see this is the shape, so this curve has a radius and that radius is called a radius of curvature. This one has a different radius of curvature, this one has a different radius of curvature. Okay, so the coordinate along the streamline, so this is a streamline, the coordinate along the streamline is S and the coordinate normal to this streamline is N. The coordinate along the streamline is called S and coordinate normal to the streamline is called N. Okay, as shown in the figure. So to apply Newton's second law to a particle flowing its streamline, we must write the particle acceleration in terms of the streamline's coordinates. By definition, the acceleration is the time rate of change of velocity of the particle. So this is the velocity, the time rate of change of velocity is called the acceleration. So here for two-dimensional flow, because we have a coordinate system S and N, or we have x or z plane, the acceleration has two components, one along the streamline and the streamwise acceleration as, and one normal to the streamline an, the normal acceleration. So streamline acceleration can be written as dv by dt. If you multiply and divide with the ds, so it will be dv by ds, the change in velocity with respect to position, multiplied by ds by dt. So ds by dt you can write down with the v. Okay, so this is the component of streamline acceleration, or this is the value of streamline acceleration. Okay, so whenever body is moving along the streamline, the acceleration value will be equal to this. Whenever the body is moving normal to the streamline, so the acceleration component will be equal to v square over r. So this is the acceleration normal to the streamline, and this is the acceleration along the streamline, and this acceleration is basically is the acceleration when the flow is a steady flow. Okay, so here there is some various flow versus acceleration. There is some relationship we have developed. Okay, what are the type of flow and what should be the value of the radius of curvature and the change in velocity with respect to position. So here we are going to develop some relationship. So if the line is straight, if the streamlines are straight, there is no curvature, in that case the radius of curvature would be infinity. Okay, so if you apply the if you insert these values in the streamline acceleration and the normal acceleration formula, you will get both streamline acceleration and normal acceleration equal to 0. In that case, you can see the radius of curvature is infinity. The radius of curvature can be infinity only when the streamline is straight, constant. There is no difference. You see the difference between the two lines, the change in velocity with respect to position, with respect to s, there is no change, is all constant everywhere. So this change is 0. So if this is 0, this is infinity, as and an both will be 0. Okay, so here you can see the line is straight, but the position is changing, the velocity is changing with respect to position. So in that case the line is straight, that means the radius of curvature is infinite. So in that case an is 0, but as will not be 0, it will be greater than 0, because the del v by del s is not equal to 0. Okay, so this is converging. Okay, we will see the reason why it is converging. Okay, now the third case, here you can see there is a streamlines and it has a curvature, but there is a constant distance between the curvatures, or between the curve path is probably available. So this is del v by del s is equal to 0, because there is no change in velocity with respect to s, with respect to position. Okay, but the curvature is not equal to infinite, because it has some curvature, it has some radius. Okay, so that's why an will be greater than 0 and as will be equal to 0. Okay, and in that case you can see both the streamline acceleration and the normal acceleration will be greater than 0, because there is a change in velocity with respect to position is also varying, and the radius of curvature is also available in all the lines. So in that case both streamline acceleration and normal acceleration will be greater than 0. So here we can see that for incompressible flow, the velocity is inversely proportional to the streamline spacing. Okay, hence converging streamlines. So this is the reason, because of that the lines are converging to produce positive streamlines or streamwise acceleration that is greater than 0. So now here we are going to see we made so far we have made some assumptions to apply the Newton's second law. So the assumption and consideration we have made under the heading of Newton's second law are: the flow is inviscid, the flow is steady, the flow is incompressible, and all forces are negligible except pressure and gravity forces. So Newton's second law gives results of interaction between the pressure, gravity forces and acceleration, provide numerous useful applications, and also provides the foundation to develop important equations such as Euler equation and Bernoulli equation. Okay, so how do we apply the Newton's second law? Under the consideration of the following assumptions. Okay, when we apply these forces, what happens? To determine the forces necessary to produce a given flow, or conversely, what flow results from a given set of forces, we consider the free body diagram of a small fluid particle as shown in figure. So here consider there is a plane and there is a air streamlines are passing over it. From here we consider a small particle and we are analyzing what are the type of forces are acting on it. Because of that, this streamline is moving, and this streamline is moving. So this flow is what kind of flow? This is a steady flow, unsteady flow, compressible flow, uncompressible flow, it is compressible or incompressible flow, or it is turbulent flow, it is a laminar flow. What are the type of flow? Basically these forces determine it. So let's see and derive some equation that is called a Euler's equation. So the assumptions we have made in the previous slide is the same assumptions in this to derive this equation. So in that case we know that the forces are the vector quantities. So we are going to consider the force component that is acting along the streamline. So in that case only we are going to consider the forces acting along the streamline. So we know that there is not only the forces acting along the streamline, but there are some forces that is also acting normal to the streamline. But in that case only we are going to consider the forces along the streamline. Okay, so here consider an inviscid fluid properties. Now consider an inviscid fluid particle moving under the action of gravity as shown if del S by del N is the plane of figure and del Y normal to the figure as shown in the free body diagram. So del S and del Y are the length of the particle in the streamline and normal to the streamline direction, and del Y is the thickness of the particle in the Y direction. Okay. Okay, the free body diagram of that fluid particle is shown. For a steady flow, okay, the component of Newton's second law along the streamline. So this is the streamline direction. This streamline is making an angle theta with respect to the axis. Okay, so in the streamline direction can be written as, so according to the Newton's second law, net forces acting in the streamline direction is equal to the mass of the particle into acceleration of the particle in the streamline direction. Okay, so the mass, so acceleration in the streamline direction, that we know that is equal to del V over del S into V, that we have discussed previously. Okay, and the mass of the particle, that we know mass is equals to density times volume. So the volume of the fluid particle is del V. So this is the representation of showing the volume of the particle. Okay, because this is V and this is V, so we have to differentiate with it. Okay, so normally we show the volume like is opposite A. Okay, so here, so density times volume into the acceleration along the streamline. Okay, so here del Fs is the net resultant force in the direction of the streamline, and V is the velocity of the fluid particle. And where del M is equals to mass of the fluid particle, density times volume. Okay, mass of the element, and volume is equal to del S, del N and del Y. This is the volume of the element of the particle, fluid element of fluid particle. The gravity force on the particle can be written as, so there is a two type of force, one is the pressure force and one is the gravity force. So here in the free body diagram you can see this is the weight of the element which is acting downward. Okay, and this weight W of the element is equal to weight density time volume. Okay, so volume of the element, if you multiply with them, you will get the weight, and the weight density is equal to rho into g. Okay, so here is the free body diagram. This is the force acting normal to the streamline, so we are not considering that. This is the force normal to the streamline. We are not considering this force. We are not considering this force. Okay, so we are considering the force only along the streamline. So this is the force along the streamline, and this is the force along the streamline. So this is the pressure force. The pressure force always acting at the surface of the element or the body. So here this is the surface, okay, which is this surface is perpendicular to the streamline, but the force is along the streamline. Okay, so here, so first we are talking about the weight, gravity force, that is weight. Okay, so this is the weight. So we need the forces acting along the streamline. So this gravity force is making some angle theta with the streamline. Okay, so this is the theta. So if we make into two components, so this is the component in the direction of a streamline, and this is the component is the normal to the streamline. So here we are going to consider only these components. So let's move on to the next slide. Here you can see the component of the weight force in the direction of the streamline is equal to minus W sine theta. So here you can see this component is equal to del Ws sine theta, the weight along the streamline. Okay, into, so we can replace this delta W with gamma into volume into sine theta. So here, just for the understanding, if streamline is horizontal at the point of interest, the theta is 0. So if it is considering a straight line, so what happened? And there is, in that case, there is no component or particle of weight along the streamline. So in that case, this factor will be completely 0. Okay, because the weight will, at the end, that case the weight is acting 100% perpendicular to the streamline. Only there is one force perpendicular to the streamline. There is no component of the weight along the streamline. Okay, so here now so this is the force which is acting along the stream. This is the gravity force which is acting along the streamline. Okay, so we have finally found the gravity force, that is equal to minus gamma times volume into sine theta. Now we are talking about the pressure force. So the pressure force, we are considering the pressure at this point is P. Okay, the pressure at this point is P. So when you move to this side, so the pressure will increase. The change in pressure from this point P to what is the pressure? So this pressure, according to the Taylor series, okay, according to the Taylor series, expansion of the pressure field, the change will be equal to this. But here we are considering this change is approximately, for the simplification, this change is equal to del PS. Okay, we are not going to consider this. There is a small change from here to here, so that change is equal to del PS. Okay, so since we are going away from the point P, so the pressure will increase. So this is going to be equal to P plus del P, and this is the pressure. And what is the pressure force? Multiplied by the cross-sectional area. So what is the normal area? Delta N. So this is delta N and this is delta Y. Okay, the thickness in this direction. So this is del N and del Y is the pressure force in this direction. And this is also, this is going closer to the reference axis, so the pressure will reduce. So P minus del P, and this is the cross section area, del N over del Y. Okay, so these are the pressure forces which are acting at the surface of the fluid element. So now we are going to see what is the net pressure force acting along the streamline. So this is the pressure force is equal to the pressure force. So this is the negative direction and this is the positive axis. This is the positive direction. Okay, so first del P minus del PS into del N del Y. So this is the negative direction. So minus P plus del Ps equal to this. So when we open up, we will get my 2 minus 2 sigma Ps del N del Y. Okay. So when we simplify it, what will happen? Del Fps will be equal to del P over del S multiplied by del S, del N and del Y. Okay. So what we have done, we multiplied with the delta S and delta multiplied and divide with del S. Okay. So what happened? So this will become volume of the fluid element. So this will be equal to minus del P over del S into volume. Okay, now the net force acting along the streamline will be equal to, this is the net force along the streamline, that is equal to sum of weight gravity force plus the pressure force. So this is the gravity force that we have derived here, and this is the net pressure force we have calculated here. So this volume is common, we take it out. Okay, so we simplified further. So sigma force, so this is the net force, will be equal to acceleration along the streamline. So acceleration along the streamline is equal to this, and this is the density. So this is the equation. So here we simplified that, and finally we got this equation, and here we replace sine theta. Sine theta is equals to dz over ds. How it came? So here you can see this is the triangle along the streamline. So this is del z over del s. Okay, so this is the perpendicular, this is the hypotenuse. The perpendicular over hypotenuse is equals to sine theta. So sine theta is equals to del z over del s. So we replace del z over del s with the sine theta. So we replace this, so this become like that. Okay, here del p over del s, and we can write down this factor. This factor is equals to half of dv square over d. So if you take the derivative of this, because here the total derivative, if you take the derivative of this, so it will become 2 dv. Okay, it will become 2 dv over ds. So 2 will cancel out, and you will end up with the same value. Okay, so we replace this value with this factor here. Okay, so finally we also rearrange this whole equation. So finally we end up with, this is the equation. Okay, so this equation is basically called the Euler's equation of motion, and this equation is valid for one-dimensional flow only, because here you see the change in pressure and is only in the streamline direction. We started with the normal direction as well, but there is no normal direction, only there is a one-dimensional flow, that is the streamline direction or the S direction. All the changes are in along the streamlines. Okay, so now this is the final equation of the Euler equation. Now we are going to move on to the Bernoulli equation. So Bernoulli equation is nothing but the integral form of the Euler's equation. So this is the Euler's equation we have derived in the previous equation. You can see, so this is the Euler equation we have derived. So I took this equation from here to here. Here you can see, if I divide this equation with ds, or I will just transfer ds to the other side, we will get the equation at the beginning of the Bernoulli equation. So this equation we will get, okay, if I transfer ds to the other side, so that will be equal to 0. So now if I multiply the whole equation with if I divide whole equation with density, so this will become like this. And if I integrate this whole equation, so what will happen? So here this is the integral of dp over rho. So this d will be cancelled with the integral, and it will become half v square. This d will be because g is constant, so this d will be cancelled with the integral, so it will be dz, and finally it come with a constant along a streamline. So this equation is valid for the compressible flow, because if it is a constant, if it is incompressible flow, you can take this density outside, the flow will be incompressible. So since it is inside the integral, so if you are considering the flow is compressible, so you can keep it inside and take some function according to that. The flow is, the density of the flow is varying. Okay, so this equation is valid for both compressible and incompressible flow. So here in general we cannot integrate the pressure term because the density can vary with temperature and pressure. However, for now we assume constant density. Now we are consider the flow is compressible. In that case, P will come outside, so the density will come outside, and this D will cancel out with the integral, and it will become P over rho. Okay, P over rho. So P over rho, so if you multiply it with the rho throughout, so what will happen? So the rho will come half rho v square, and the P will become P plus, so this will multiply it with the P, so rho, so half rho v square, this will also multiply it with the rho, so rho g is equal to gamma. So gamma z is equals to constant along the streamline. So that means the Bernoulli equation a very powerful tool in the fluid mechanics. Okay, so basically it indicates the net change is constant along the streamline. Okay, the net change is constant along the streamline. So here are the assumptions that we made to derive the Bernoulli equation. Viscous effects are assumed to be negligible. The flow is assumed to be steady. The flow is assumed to be incompressible. The equation is applicable along a streamline only. Along this equation is valid for a single streamline. If you want to apply this equation onto the multiple streamlines with a different constant value, so you cannot apply this equation. To apply this equation, all the streamline has the same constant C. Then you will be able to apply the Bernoulli equation at a particular cross section, because you know that in the pipe flow and all, we applied the Bernoulli equation at a particular cross section, and at one cross section there are millions of streamline passes through. If each streamline have a different constant, so we cannot apply the Bernoulli equation. But if all the streamline has a same constant, that means we can apply the Bernoulli equation at that point. Now here we are going to see some physical interpretation of the Bernoulli equation. So what are the Bernoulli equation interpretation? So here we are going to indicate the Bernoulli equation in the form of energy, in the form of pressure, or in the form of head. So first of all, here you can see we have three factors. So here we have three, we have written the Bernoulli equation in the three form. So first, half v square is equals to kinetic energy if you multiply the whole equation with rho. Okay, so what will happen? So this is going to be P over rho. This is equal to gz. This will be equal to half v square. So half v square is basically the kinetic energy, gz is the potential energy, and P over rho as a flow energy, all per unit masses, because we know the kinetic energy is half mass into velocity square. Okay, so here the Bernoulli equation can be viewed as a mechanical energy balance and be stated as the sum of the kinetic energy plus potential energy and the plus flow energy of a fluid particle is constant along a streamline during a steady flow when the compressibility and frictional effects are negligible. Okay, so here if all the energy at one point is equal to the energy at other point, yani if the fluid is moving from one point to another point, its total energy is conserved. Its total energy is conserved. So that's why we can equate P1 is equals to rho v1 square plus gamma 1 z square is equals to P2 plus rho v2 square plus gamma z2 is gamma z2. So we can equate all the energy at one point is equal to energy at the other point. So now here we are going to write down the equation in the form of head. Here you see this is the z is the head, this is the, here you can see the elevation term z is related to the potential energy of the particle and is called the elevation head. So this is z is called the elevation head. Okay, the pressure term P over rho is called the pressure head and represents the height of the column of the fluid that is needed to be produce the pressure P. So this is basically the static head. Okay, So this is also in the form of a head. If you simplify the unit, you will end up with in the form of meter. This is the velocity head. Okay, this is the velocity pressure. We will write down in the form of pressure, but this is the velocity head. When you will simplify the unit, you will end up with the in the form of a unit of length. So the velocity of v square over 2g is the velocity head and represents the vertical distance needed for the fluid to fall freely, neglect friction. If that means that we are considering here the ideal flow, we are not considering any friction or incompressible or compressibility. If it is to reach velocity v from rest. So the Bernoulli equation we represented here in the form of head. Okay, now we are going to represent the Bernoulli equation in the form of pressure. Okay, in the form of here the Bernoulli equation states that the sum of pressure head, the velocity head and the elevation head is constant along the streamline. Okay, so here we can see that. Okay, so this is basically the form of energy. Okay, now this is the form of the pressure. This is the form of pressure. Okay, the Bernoulli equation we have written in the form of pressure. So this is the pressure, this is the static pressure, this is the dynamic pressure, and this is the hydrostatic pressure due to the head. So sum of the kinetic, so here you see this is the Bernoulli equation in the form of kinetic energy. The sum of the kinetic, potential and flow energies of a fluid particle is constant along the streamline during a steady flow when the compressibility and friction effects are negligible. This is written here, but this is the form of pressure. This is Newton per meter square, this is also Newton per meter square, this is also Newton per meter square. Here what is the unit of energy is the joule. Here what is the unit of meter, that is meter. So when you will simplify that, you will get the unit meter. When you simplify this, you will get the unit joule. When you simplify this, you will get the unit Newton per meter square. So here is the physical interpretation of the Bernoulli equation. But now we are going to see one example, the kinetic potential energy, how the energy changes. By using the Bernoulli equation we can easily analyze. So we have point 1, point 2 and point 3, and we are considering there is a streamline. So if you apply the Bernoulli equation at point 1, point 2 and point 3, so we will end up with the type of energy we have at this point 1 and how the energies are changing from one form to the another form, but the net energy is constant at every point. Okay, the net energy what we have at this point is at same at this point and same at this point. What's happening? Only the shape of the shape or type of the energy is changing from point at point 1. Here you see the kinetic energy is small because here the velocity is very low because the size of the container or the size is diameter is big. Okay, here the potential is energy is 0 because there is Z is 0 here, so there is no potential energy at this point. Here the static pressure is large because we compressed, so this liquid is pressurized within this container, so because of that the static pressure is very high. Okay, so when you move to the point 2, so this energy converts into different form. So at point 2 the kinetic energy is large because this is the area is less, so this is acting like a nozzle. So at the nozzle we have a very high velocity, so because of the high velocity we have kinetic energy is very high. So here the potential energy is small because we have some depth from here to here to the fluid. You can see there is a height of the fluid that can work from here to here, so the potential energy is small. But the pressure here, because the pressure here is atmospheric pressure, so that means the pressure the static pressure is 0 at point 2. Okay, so now move on to the point 3. At point 3 there is no kinetic energy. You know that it is stopped here, so velocity is 0 at point 3, so the kinetic energy is 0 and potential energy is maximum because you have a maximum height available here, so the potential energy is maximum and the static pressure is same the atmospheric pressure, so it is going to be 0. So I think you will completely understand. Now move on to one small concept. So Bernoulli, the application of Bernoulli equation, the simplest case of the Bernoulli equation, okay, when P is constant, or P is equal to 0 or constant. Okay, if the pressure is 0 and constant, so what will happen is with the Bernoulli equation, this is the simple case of the free jet. Okay, this is a simple case of free jet. So what is the simple case of free jet? In the case of free jet, the pressure is known. The pressure at every point is atmospheric pressure, that is constant, or there is no pressure. So if you consider the pressure here, you see there is atmospheric pressure. Pressure here is atmospheric pressure. Here pressure is here, atmospheric pressure. Pressure here is atmospheric pressure. In other case also, the pressure here is atmospheric pressure that you are pouring it, and also at the exit the pressure is atmospheric pressure. That means the pressure is same at the inlet and exit. So if you apply the Bernoulli equation at 2 points, you can easily find out the velocity here and the velocity here. Okay, so here the pressure is same, so they are cancel each other. So if you simplify that, the V2, if this is the point 1 and this is the point 2, the V2 velocity you can calculate. If this velocity is 0, so you can, this factor will be 0, and only the velocity will, the potential energy will convert into the velocity head. So this is basically the simplest case of the free jet. When the either pressure is constant or 0, this will give you the free jet condition. So this is the end of the today's lecture.